Okay, we are going to continue with the August 2019 exam, but now we're moving on to the answer booklet questions, so part B2 and C. Okay, so we're going to need to write our answers in the answer booklet. Remember, we can use this space in the test for any of our notes, but we're going to want to transfer all answers over here, so I'll model that process. Okay, so we have our first group of questions, 51 through 53, based on this. State the number of protons in an atom of N15. Well, I don't really care if it's N15 or N100. Well, N100, it's not really going to be a thing, but it doesn't matter if they ask me about N14 or N15. Number of protons has to do with what element it is. The element is nitrogen. So on the periodic table, nitrogen always has 7 protons because that is its atomic number. So 7 protons. Okay. State the number of electrons in each shell of a nitrogen-14 atom in the ground state. Again, it doesn't matter if we're talking nitrogen-15 or nitrogen-14. We're going to get that information from the reference table, from the periodic table. Here is the electron configuration. It is 2-5. So I'm going to jot that down. 2-5. What does that mean? That means I have 2 electrons in the first energy level and 5 electrons in the second energy level. The first energy level, closer to the nucleus, has less energy, and the second energy level, further away from the nucleus, has more energy. Didn't ask me about that, but that's just a little side note. So our first shell had 2 electrons, and our second shell had 5 electrons. Okay, 53. Based on the atomic mass of the element nitrogen on the periodic table. So before go any further, let's look it up. 14.0067. So based on this number, compare the relative abundances of the naturally occurring isotopes of nitrogen. It says the naturally occurring isotopes are these 2. When it says compare, again, we either need to talk about them being equal, one is greater than the other, or one is less than the other. All right, let's look. This is the atomic mass of nitrogen on the periodic table. Shockingly, or perhaps not shockingly, what is that very close to? That's very close to 14, isn't it? So that means nitrogen-14 must be the more abundant isotope because the atomic mass of nitrogen is so close to 14. So the relative abundance of nitrogen-14 is much greater than the relative abundance of N15. It just has to be that way, right? Because the atomic mass is closer to N14. All right, so I'm going to turn page in here, my answer booklet. But here, I'm just going to continue down to my next set of questions, which is 54 through 56. Again, we can skip the reading. This is short reading, though, so I'm just going to look at it. The melting points and boiling points of 5 substances at standard pressure are listed on the data table below. Identify the substance in this table that is a liquid at STP. Well, notice all of these temperatures are listed in Kelvin. STP in Kelvin is 273 Kelvin. All right, so in order to be a liquid at STP, 273 has to be between these two numbers because below the melting point, substances are solids. Between the melting point and boiling point, substances are liquids. And above the boiling point, substances are gases. So that means 273 has to be between these two numbers. Let's see if that's true. Nope. 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 Wait. There we go. Okay, so the substance that is a liquid is going to be bromine, or I could write Br2. And we should know that bromine and mercury are the two substances on the periodic table that are liquids at STP. State in terms of the strength of intermolecular forces why I2 has a higher boiling point than F2. Okay, so it says in terms of intermolecular forces. That means my answer must talk about intermolecular forces. So why does I2 have a higher boiling point than F2? Because I2 has stronger intermolecular forces. So I2 has a higher boiling point because it has stronger intermolecular forces. Okay? State what happens to the potential energy of a sample of NO liquid at 121 Kelvin as it changes to NO gas at constant temperature and standard pressure. So when you go from a liquid to a gas, so when I go this way in changes of state, potential energy is going to increase as we go this way. That means the particles have more potential to move. They're held real tightly in a solid, right? In a liquid, they're a little looser. In a gas, they're very far apart. So potential energy increases as we go this way. So as we go from a liquid to a gas, the potential energy is going to increase. So that's not a complicated answer. The potential energy increases as NO changes from liquid to gas. Be clear enough in your answer that people understand what you're talking about. If you're too vague, can't give you credit. Notice I didn't say a lot of it and they, because that gets confusing. All right, now I have to turn the page here. And we're moving on to question 57. So 57 through 59 are in this section. Using the information on table B, determine the amount of heat absorbed by the water when the water is heated from 20.0 degrees Celsius to 50.0 degrees Celsius. First, I need a heat formula. I have a change in temperature, so there's my formula. Q equals mc delta T. My mass, 100 gram sample. C, well, it told me I needed table B. I need table B for this, for the specific heat capacity. So that's 4.18. And my delta T is my change in temperature. So I'm going to subtract these two temperatures. And I get what? 50 minus 20 is 30. Alright, I'm just going to clear this focus up a little bit as I'm getting my calculator. So let's turn this on. Okay, and we need to do 100 times 4.18 times 30. What does that equal? 12,540 joules. There is my answer. 12,540 joules. Okay, so I have to make sure I put that on the correct line. Alright, now we go here. Based on table H, determine the vapor pressure of the water sample at its final temperature. Alright, so what was its final temperature? 50 degrees Celsius. So go to table H. At 50 degrees Celsius, what is the vapor pressure of water? So I got to use the right line, right? This is the correct line for water. All right, that's ethanoic acid. There's water. So go across from there. I'm going up by 10 on these lines. So I'm not at 15, probably about 12. All right. So 12 kPa. Just so you know, on the answer key, you are given credit for between 11 and 13. So I said 12, but if you had said 11, 12, or 13, you would have been accurate. And based on table G, determine the mass of KClO3 solid that must dissolve to make a saturated solution in 100 grams of water at 50.0 degrees Celsius. All right, so first of all, go to the right table. All right, so here we are, table G. What substance do we have? KClO3. So that's right here. And what's the temperature? 50 degrees Celsius. So again, KClO3, 50 degrees Celsius. So I'm going to go up from 50 degrees Celsius until I hit KClO3's line, which is going to be right there. Okay. Now this is 20, this is 30, this is 25. So it's definitely under 25. I'm going to say 21. Okay, so at 50, I'm going to say 21 grams because saturated is on the line. What do you want to know for the exam? They are giving you credit for between 20 and 23 grams. So you had some leeway. Okay. All right, now we're on to the next question set, and that has to do with an electrochemical cell. So let's just figure out some information about this electrochemical cell before we even go to the questions. This is my suggestion. So my two metals are Cu and Cr. So I look at table J. It says a voltaic cell, which is a battery, and this takes chemical energy and converts it into electrical energy. All right. So Cu and Cr. Well, Cu is real low down here. Cr is right here. Cr is higher, so that means it's more active. In terms of metal, that means Cr is a better loser, so that's Leo. Copper is going to gain, that's Gur. And if you remember An, Ox, so that's over here. Red cat. Okay, so An, Ox means this is the anode, which has a negative charge. This is the cathode, which has a positive charge. Since this is losing electrons, the mass goes down because the atoms go down. The ions will go up. So what will happen is atoms of this metal will lose electrons and then end up in solution as the ions. The opposite thing will happen over here. The ions in solution will gain electrons to become atoms. So this piece of metal gets bigger, this piece of metal gets smaller. When this piece of metal runs out, the battery no longer works. Electrons always flow through the wire from anode to cathode. Ions flow through the salt bridge, keeps the cell neutral. Okay, that's a lot of information, so let's see if any of it helps us with the questions. Identify the subatomic particles that flow through the wire. Well, that should be easy. That's electrons. Electrons flow through the wire. State the purpose of the salt bridge in completing the circuit in this cell. Okay, so the salt bridge allows ions to flow back and forth to keep the cell neutral. Okay. 62. Write a balanced equation for the half reaction that occurs in the copper half cell when the cell operates. So I'm going to use this whole thing as a guide, but it says on the copper. So I'm only going to write down the copper part, and I'm going to ignore the others. So I have 3 Cu2 plus yields 3 Cu. Okay, so remember this, what we did before. As we move this way on the number line, that's Leo. This points to the side of the equation that the electrons belong on. This way is Ger. This points to the side of the equation the electrons belong on in this case, okay? So what's important to note is this equation had 3 CUs. So first what I need to do, going from a +2 to a 0, how many electrons is that? Well, that's 2 electrons, right? But each copper is going to gain 2 electrons. But I have 3 coppers, so each copper gains 2, right? Or we could think about this another way. So the charge of this is 0, 3 times 0 is 0. The charge of this is +2, 3 times +2 is +6. We cannot have that imbalance, okay? I need to find a way to make this side also 0 like this side, okay? Now you could say, why can't I make this side equal +6? Well, the only thing I can do is add electrons in somewhere. So if I'm adding in negatives, all that's going to happen on this side is going to make it more negative, which worsens the problem. So remember how I said there were 3 CUs, and each CU gained 2 electrons? So 6 electrons. So that would be -6, and then a -6 and a +6 does equal 0. Charge is balanced. So I can write it like this. 6 electrons plus 3 Cu plus 2 yields 3 Cu. Okay? Now, if you wrote it using 1 copper, you would write it like this, and you would get credit for it. I wrote it like this because that is how the equation was started. But this is also a correct answer, just so you know. All right, so I'm going to turn this over. All right, so we have this section right here. Determine the molarity of the HCl sample using the titration data. So I need a formula. That's this one. MAVA equals MBVB. Remember, it's the molarity of H plus and the molarity of OH negative. Double checking my bases and acids, 1 OH, 1 H plus. So that makes it easier. So MAVA equals MBVB. So an NaOH solution with a pH of 13 is used to determine the molarity of an HCl aqueous solution. A 10 milliliter sample of HCl, so that is VA 10.0, is exactly neutralized by 16 milliliters. That is the VB of 0.100 molar. So MA is what I'm trying to find. So what do? Multiply these two together. 0.100 times 16 equals 1.6 equals MA. That's 10.0. Take 1, divide both sides by 10.0. MA equals 0.16 molar. Okay? 0.16 molar. Compare the hydronium ion concentration to the hydroxide ion concentration when the HCl solution is exactly neutralized. So when it is exactly neutralized, the pH is 7. So let's look at a pH scale real quickly. We have 7, 0, 14. I don't know why I put the arrows there. Here's acid, here is base, there's neutral. As we move this way, H plus goes up, we get more basic. Oops. H plus goes down. It gets more basic, less acidic. As we go back this way, H plus goes up. Sorry about that. And we get more acidic. at 7, okay, we have equal amounts of H plus and OH negative. So as we go this way, OH negative would go up, OH negative would go down. So that means at a pH of, as we get lower here, the H pluses are going up and the OH negatives are going down. So we have very few OHs and lots of H pluses. On this side, going toward 14, we have lots of OH negatives and very few H pluses. At 7, they're equal. Now, why are they saying hydronium ion? Okay, because an H plus and a water molecule make an H3O plus. So usually the H plus sticks to water and looks like this anyway. So at a pH of 7, when it is exactly neutralized, the hydronium ion concentration and the hydroxide ion concentrations are equal. So the hydronium ion and hydroxide ion concentrations are equal. All right, one last question in this one. Determine the pH value of a solution that has an H plus ion concentration 10 times greater than the original NaOH. Well, what was the NaOH? 13. Okay, so here's 13 right here. If we have a solution that has a H plus ion concentration 10 times greater, so which way do I move? If it's 10 times greater, since this is a logarithm scale, one jump on the number line is times 10. So it can either be 14 or 12. Those are your two options. If the H pluses are increasing, I need to be moving this way, so that means it's going to be 12. All right, let's turn the page. We're moving on to C. We finished B1, but we're still working on the written questions. All right, so I'm going to skip this reading. It's for 66 through 68, and I'm going to go to the questions. I'll probably need some information from here, but let's just continue. Explain why the sample in the crucible was heated repeatedly until the sample had a constant mass. Okay, I guess I better read. A hydrate is a compound that has water molecules within its crystal structure. Magnesium sulfate heptahydrate, here's the formula, is a hydrated form of magnesium sulfate. The hydrated compound has 7 moles of H2O for each mole of MgSO4. When 5.06 grams of MgSO4 with 7 H2Os are heated to at least 300 degrees Celsius in a crucible by using a laboratory burner, the water molecules are released. The sample was heated repeatedly until the remaining MgSO4 had a constant mass of 2.47 grams. During this laboratory activity, appropriate safety equipment was used and safety procedures were followed. Okay, so we have the MgSO4 in the bottom of a crucible, right? And the MgSO4 has water molecules in it. So as we start to heat it, so here's our flame. As we start to heat it, the water is going to evaporate. We might not get all the water out at first. So if we heat it again and the mass goes down, that means there was still water left to leave. So if we keep heating it and the mass finally stays constant, that means all of the water was removed, right? All of the water was removed from the hydrate. So we continue to heat it to make sure all of the water is gone. Okay, so repeated heatings ensure all the water is evaporated. Okay. 67. Using the lab data, show a numerical setup for calculating the percent composition by mass of water in this hydrated compound. So let's get the formula. Percent composition by mass. All right, so we can see it right here. Mass of part over mass of whole times 100. Okay, so percent composition is mass of part over mass of whole times 100. Now here's the thing, I do not have to do any calculations. All I have to do is plug the right numbers into this formula. So the mass of the whole thing was 5.06 grams of the hydrate. That's what I started with, 5.06 grams of the hydrate. Don't forget the times 100. So what is the mass of the part? I want to calculate the percent of water. Well, the water was what was removed, right? So this, which is left, is not the water. So how do I find the mass of the water? I take 5.06 minus 2.47. Okay, so 5.06 is what I started with, minus 2.47. That was what was left. So that tells me how much water was actually in the compound, divided by the whole thing times 100. Now I stop there. That's it. Done. Okay. Determine the gram formula mass of the magnesium sulfate heptahydrate. Okay, so it is MgSO4 7H2O. Okay, so gram formula mass. Magnesium, sulfur, oxygen. Magnesium is just 1, sulfur is 1, oxygen 4. Then we have hydrogen and oxygen again. 7 times 2, we have 14 hydrogens there, and 7 times 1, we have 7 oxygens there. Times our gram formula mass. Okay, oxygen you should know is 16, hydrogen is 1. Sulfur and magnesium, maybe you have to look those ones up. So I'll do it with you just to be sure. Right, you shouldn't have known hydrogen was 1, oxygen is 16. So sulfur is 32.1. And magnesium over here is 24.3. So that's 24.3, 32.1. 4 times 16 is 64. 1 times 14 is 14. And 7 times 16, I think that's 112, but let's check it. 7 times 16 equals, I was right, 112. Now I'm going to add all those up. So 112 plus 14 plus 64 plus 32.1 plus 24.3 equals 246.4. Okay. So that is what I put here, 246.4. Now, just so you know, you are given some leeway here from 245.989 to 247. So depending how many decimals you used, your number may be slightly different. So you're given a little bit of flexibility here. Okay. So let's move on. We're on to 69 through 71. Here we have some reading. Let's go to the questions first. State in terms of electrons. So my answer has to talk about electrons. Why the radius of an Na plus ion in the table salt is smaller than the radius of an Na atom. Okay, so when Na becomes an Na plus ion, it loses 1 electron. When it loses an electron, think logically, the size gets smaller. Okay, so the Na plus ion is smaller, and Na atom loses an electron to become an Na plus. Okay? What you have to be careful is don't ever say the Na plus ion loses an electron, because it doesn't. The atom loses the electron and becomes the ion in this case. All right. Identify the noble gas that has atoms with the same number of electrons as a chloride ion in table salt. Well, a chloride ion is Cl negative. So let's go here. chlorine is right here, has 17 electrons. Cl negative means it's gained 1 electron, and ding, 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 it has the same number of electrons now as argon. What would sodium do? Well, sodium lost an electron, right? So if sodium was right here, it had 11, it loses 1. It would have the same number of electrons as neon. In the space in your answer booklet, draw a Lewis electron dot diagram of a Cl2 molecule. Well, chlorine has 7 valence electrons, so its electron dot diagram looks like this, but I have 2 of them, right? And they're going to bond together. So what will that look like? Chlorine bonded to a chlorine, and then these electrons that are already paired are going to stay there. You cannot leave them off, so it should look like this. Okay? All right. We are moving right along. We're 72 through 75 for right here. State what happens to the average kinetic energy of the gas molecules if the cabin temperature decreases. Well, temperature is a measure of average kinetic energy. So if the temperature decreases, the average kinetic energy decreases. Okay, so I didn't even need any of that reading yet. So the average kinetic energy decreases when the temperature decreases. So notice how my answer is very clear. Don't be vague. Don't use this it's and they. Okay? Convert the original air pressure of the cabin of the submarine to atmospheres. So the enclosed cabin of submarine has a volume of this, a temperature of this, and a pressure of this. Okay, so it is 116 kPa, and I want to convert that to atmospheres. How do I do this? Well, right here is my conversion. 101.3 kPa is the same as 1 atmosphere. So I'm going to set that ratio up. 101.3 kPa equals 1 atmosphere. So I don't have 101.3 kPa, I have 116 kPa's equals how many atmospheres? Now I cross multiply, right? 1 times 116 is just 116 equals 101.3, and this is my x, right? X. Instead of writing question mark atmosphere, I should have written x. That would have made it less confusing. Now I'm going to divide both sides by 101.3. Since 116 is higher than 101.3, this answer better be larger than 1, right? So let's make sure. 116 divided by 101.3 equals, it is 1.15 atmospheres. Okay? So I converted it to atmospheres. Alright, let's move on. And we are 76 through 78 right here. And on the labeled axes in your answer booklet, draw a potential energy diagram for the reaction represented by this equation. So here is this equation. Okay, so no wonder I was confusing myself. Okay, for some reason, I just pretended that 73 and 74 didn't exist. So let me pause for a minute and let's go back. 75, which I just did this work, is 1.15 atmospheres. Just so you know, the Regents exam gave you some leeway for 1.14 to 1.16. Okay? And I totally skipped 73 and 74, so what I wrote here for 73 is definitely not right. So I'm going to have to kind of do it to the side. Show a numerical setup for calculating the pressure in the submarine if the cabin temperature changes to 293. So this is combined gas law. Remember this formula? So I'm going to have to do this down here. P1 V1 over T1 equals P2 V2 over T2. Okay. So let's go. Enclosed cabin, a volume of 2.4 times 10 to the 5th liters. So that's V1, pressure of 116. So 116, 2.4 times 10 to the 5th, and a temperature of 312 equals, I'm calculating pressure, so that's P2. What is V2 is it didn't change. So I can just write it again, 2.4 times 10 to the 5th. Or in reality, I could have left it out, but we'll talk about that. It's changed to 293. So this is one correct way to write it. Or since you realize these numbers are the same, I could simplify this to 116 over 312 equals P2 over 293. Just like that. Okay? All right. 74. Determine the number of moles of CO2 in the submarine cabin at which the air becomes unsafe to breathe. The gram formula mass of CO2 is 44.0 grams per mole. So in order to do moles, I need this formula. Mass over gram formula mass. So moles equals mass over gram formula mass. Air in the cabin becomes unsafe to breathe when the mass of CO2 in this cabin exceeds this number of grams. So 2156 grams divided by the gram formula mass is 44. Okay. And that should give us our number of moles. So you probably don't know how to do that in your head. So what are you going to have to do? Use a calculator. Right? So 2156 divided by 44 equals, oops, what did I do? 2156 divided by 44. 49 moles. 49 moles. Okay, now for real, we're on to this section. So I had to show a potential energy diagram. Here's what I need to know. Do you see this? Heat is on this side. When heat is a product, it is exothermic. So all I have to draw is an exothermic diagram. So I start with the reactant, I go up with the activated complex, and then with exothermic, my line here has to be lower. That's it. That's as simple as it is. Okay. For 77, compare the activation energy of the catalyzed reaction to the activation energy of the uncatalyzed reaction. So let me just make a note down here. If here is my potential energy diagram, and this represents a catalyst, you can see the reactant's potential energy remains the same. The product's potential energy remains the same. The activated complex remains the same. But the activation energy changes, and it is lower when you have a catalyst. So when a catalyst is added, the activation energy is lower. Okay? Number 78. Determine the number of moles of O2 required to completely react with 28 moles of CO2 during this reaction. So I have a balanced equation, which it tells me right here. All right, so I'm starting with 28 moles of CO. And I want to convert to moles of O2. So I need moles of CO down here. Where do I find these numbers? From the coefficients. So what is the coefficient in front of CO? 2. In front of O2? 1. So I take 28 times 1, which is 28, divided by 2, which is 14. So 14 moles are required. All right, we're getting close to the end. 2 last question sets. All right, so here for this one, identify the element in propene that is in all organic compounds. Well, here's propene, but I don't even need to know that. All organic compounds contain carbon, period, end of story. Explain in terms of chemical bonds. So I have to talk about chemical bonds. Why the hydrocarbon reactant is classified as unsaturated. Why is this unsaturated? Because it has a double bond between 2 carbons. Okay. The reactant, I don't want to say it or they because that can be confusing. We might not know what you're talking about. The reactant is unsaturated because, remember, I got to talk about chemical bonds. It has a double bond between 2 carbons. Okay, easy peasy. Write the general formula for the homologous series to which propene belongs. So now I go back to my reference table and I look at table Q. Propene is an alkene. There's the general formula. That is what I write. Exactly that. Can't see it. CnH2n. Ta-da. All right, now my last question set right here. Compare the first ionization energy of argon to the first ionization energy of helium. So again, remember I skipped this reading because if you notice, sometimes I literally don't even need it. So first ionization energy is here. So argon's first ionization energy is 1521. Helium's first ionization energy is 2372. So compare, remember, means either they're equal, one is greater, or one is less. So the first ionization energy of argon is greater than the first ionization energy of helium. Okay. So I had no its, no theys. Perfect. State evidence from the passage that gamma radiation has greater penetrating power than alpha or beta radiation. So now I do have to go to the reading because whatever I state has to be in the reading. Radioactive emissions can be detected by a Geiger counter. When radioactive emissions enter the Geiger counter probe, which contains a noble gas such as argon or helium, some of the atoms are ionized. The ionized gas allows for a brief electric current. The current causes the speaker to make a clicking sound. To make sure that the Geiger counter is measuring radiation properly, the device is tested using the radioisotope cesium-137. So far, nothing yet. To detect gamma radiation, an aluminum shield can be placed over the probe window to keep alpha and beta radiation from entering the probe. A diagram that represents a Geiger counter is shown below. So what that means is to detect gamma radiation, an aluminum shield can be placed over the probe window. So there's the window. to keep alpha and beta radiation from entering. That means alpha and beta radiation can't go through the aluminum, but gamma can. So state evidence from the passage that gamma radiation has a greater penetrating power than alpha or beta radiation. Gamma radiation can pass, what did they call it? An aluminum shield can pass through the aluminum shield, but alpha and beta cannot. All right, 2 last questions. Determine the time required for a sample of cesium-137 to decay until only 1/8 of the original sample remains unchanged. So if we start with 1 as the amount, after 1 half-life, we have a half. After another half-life, it's a 1/4. After another half-life, it's an 1/8. So how many half-lives did that take? Remember, we don't count this, that's our starting point. So 1, 2, 3 half-lives. So what I need to know is how long is the half-life of cesium-137. So let's look at table N, and let's find cesium-137. Its half-life is 30.2 years. So 1 half-life is 30.2 years, but we had 3 half-lives, right? So 30.2 times 3, 90.6. 90.6 years. Complete the nuclear equation in your answer booklet for the decay of cesium-137 by writing a notation for the missing product. Okay, so remember, whatever's on the top on this side has to be the same on this side. So I have 137 on this side. I have 0, so that means 137 needs to be on the top. The bottom I have to be careful. There's 55 on this side and -1 on this side. So 55 equals -1 plus my missing number. Add 1 to both sides. Okay, because of the negative, we have to be careful. Now I need a symbol. I can't just leave it like that. That's like having house numbers and no house. That's silly. I need to look up 56. So 56 is right here. Barium. So there I have completed the nuclear equation. And that is it. That is the end of the exam. So we did all of the written response, all of the questions that are in the answer booklet.